Let's start with our first PIT problem. This is really not that different from anything else you've done, but you are asked to add 20 units of oxytocin to 1 liter of normal saline. The oxytocin looks like this. Okay, let's turn it so you can see. Very clearly on the label it says 10 units per ml. You can use it IV or IM. We need 20 units in a bag of normal saline. Okay, so how many mLs will you add to the bag? Very simply, 20 over X mLs equals 10 over 1 ml. Ratio proportion, you cross multiply. So 20 equals 10x, solve for x, equals 2 mLs. You need 2 of these little vials, okay? 2 mLs of oxytocin. And that's how that works. Okay, so this is our next PIT problem. The nurse is initiating an oxytocin induction. The protocol at this hospital is to start at 1 MU per minute and increase by 2 MUs per minute every 60 minutes until adequate labor is achieved. But we're initiating the infusion, so the only numbers we're really concerned with at this point are the 1 MU per minute, right? So at what rate in mLs per hour will the nurse set the pump if the premixed bag has 30 units of oxytocin, 500 mLs of LR? Okay, so let's start with our dimensional analysis. I'm going to try and write kind of small. It's hard for me to do that on this device, but okay. So with dimensional analysis, you start where you hope to finish. You're going to hear me say that a couple times. Set up as many problems as you want in this format to get really comfortable with it. And if you want mLs on the top, you put all your mLs on the top. If you want your hours on the bottom, all your hours on the bottom. Well, we know we have MUs and minutes and units and mLs. We want to get rid of these minutes because they're not in our answer. So keep the hour on the bottom and put 60 minutes up top. Okay? All right, we know we have mLs on the top. We have a 500 ml bag that has 30 units. We want 1 MU per minute, so we'll put 1 MU per minute. And we need to somehow convert those units to milliunits. So let's go ahead and make 1 unit equal to 1,000 milliunits. Okay, now that we've set it all up, we've got all the important numbers in there. Okay, we can start canceling out the things that we really don't need. All right, we don't need units, so get rid of units. We don't need millunits, so get rid of millunits. We don't need minutes, so get rid of minutes. And then what we're left with here is mLs per hour, which is what we want. So now all we have to do is multiply across. This is the point where some of you might reduce your fractions, but you don't have to. So what we're going to end up with is 30,000 mLs over 30,000 hours. Okay, so solve that any way you want to. It's going to come out to 1 ml per hour equals 1 MU per minute. Okay, and that sort of illustrates our point. That concentration is going to be a 1-to-1 ratio, but 1 mLs per hour is our answer using dimensional analysis. Okay, so this is another PIT math problem, and this is more what we were confused about the first time we met in class. All right, and we're going to work it out simply, but I hope you watched the lecture on medical management of labor and delivery, and you saw a lot about oxytocin, induction of labor, because you're going to see that 30 units in 500 bag over and over again. Those of you who understood the lecture are going to look at this problem and know the answer without doing any math, which is the intent of having a bag in that strength. But let's work it out in dimensional analysis. In dimensional analysis, You start where you hope to finish. So we want to know what the pump rate is. Pump rates are always set in mLs per hour, right? Okay, we don't know how many mLs per hour yet, but we know we want all of our hours on the bottom and all of our mLs on the top, and any other variable in here needs to cancel out. So let's start with hours. How many minutes are in an hour? Because we have minutes in this problem. We don't need minutes, we need hours. So 60 minutes is in an hour, right? Our hours are still on the bottom. Now we need to cancel out minutes, and we have a infusion order or desired of 5 MUs per minute, and that's going to help us cancel out our minutes. And now we have this bag that's 500 mLs equals 30 units. Okay, we want our mLs on the top because here's our mLs on top, our hours are on the bottom. So let's put our 500 mLs up here and our 30 units down here. 30 units is also the same as 30,000 millunits because we have millunits up here. We could make that a separate factor if we wanted, but I'm running out of space and I think you understand that concept. So now our problem is set up, okay? We can start canceling out the units that we don't need. We don't need minutes, so we can cancel those out. We don't need MUs. We can cancel those out. Now, those of you who don't like to reduce fractions, just multiply straight across. We have 60 times 500 is your 30,000, times 5 would be 150,000. It's a lot of zeros, making me nervous, but it's okay with me if you don't really want to do that. We have 30,000 down here. Okay, now you are going to have to reduce that fraction or at least do some division, but it makes more sense to me. At least get rid of your zeros. You end up with 15 over 3. Now, if you have to whip out your calculator to know that that is 5, that's fine with me, but you could have reduced the fraction. It would just be simpler. 5 mLs per hour equals 5 MUs per minute. And that pretty much tells you exactly what I said in the lecture, which is that bag has a 1 mL per hour ratio to MUs per minute. It's a 1-to-1 ratio, so you don't really have to think about it. So when you get an order that says start at 1 and increase by 2, it's a 1-to-1 ratio. You're just adding and subtracting. I'm starting at 1 mL per hour. I'm increasing to 3 mLs per hour. Then I'm increasing to 5 mLs per hour. Then I'm increasing to 7. So that's much, much easier than having to do a lot of this sort of complicated dimensional analysis or ratio proportion. So that kind of tells you how that math is done. Now, on somebody else's exam, say an ATI exam, you might see different concentrations, and you can certainly work it out that way. But my emphasis has always been on critical thinking. You might not even see too much pit math. You will see other math that does require you to make calculations, but that's how it's done. Okay, we're going to go on to another problem. Okay, so this is one of those things. You walk into a room, you haven't gotten a report yet, but you see that your pump is set to 45 mLs per hour. You want to know how many MUs per minute that patient's receiving because that's how you're charting it. Maybe you got report and she said, I can't remember the number that the pit's at. Now, usually, I don't think anybody ever forgets what their pit's at, but whatever. So this person is getting a bag that has 20 units of oxytocin in 1,000. That was another one of our standardized concentrations. Okay, so how many MUs per minute? We want to know, let's go in dimensional analysis, we want to know how many MUs per minute that patient is receiving. So we start where we hope to finish. We start with the answer. We want all of our MUs on the top and all of our minutes on the bottom. So now we need our minutes to be on the bottom. We know that 60 minutes is in 1 hour, right? Okay, so now we have, we want to get rid of our mLs and have our millunits. So let's put our units. Well, we know that 20 units is 20,000 millunits, so let's get our 20,000 MUs up top. And we have our 1,000 mLs on the bottom, okay? And we are at 45 mLs per hour, so we want to get rid of the mLs anyway, so let's keep our hour here, okay. Now let's cancel out the units that we don't need. Switch colors here. Cancel out the hours, they're not part of our answer. Cancel out the mLs, they're not part of our answer. Now we have MUs per minute, which is what we wanted, which is what's over here, okay. Now those of you who don't like to reduce fractions, again, multiply straight across. You are going to end up with 9, oh Lord, is it 900,000? Jeez Louise, I'd be so happy to reduce that. Over 60,000. Let's at least get rid of some zeros here. Oh boy, so 90 over 6. You can divide that using the division factor on your calculator. You just could have reduced fraction. You'll still come out with the same answer of 15 MUs per minute. Okay? Now if you remember, we looked at that bag in the lecture that I referenced earlier, and we said that that 20 units in a liter has a standardized concentration of 3 mLs per hour to 1 MU per minute, which corresponds roughly to this. So if you want to work it out, work it out. If you want to use the, the easy peasy way, do that too. That is completely up to you. But that's about as fancy as pit math should get. Now, something I might do just to be tricky. I could have a problem that said something like, here, let me just erase my board here. In report, the outgoing nurse tells you that her pit is at 14 MUs per minute. You walk into the room and you see the pump rate set to 45 mLs per hour. Was this correct? And doing the same math that we just kind of discussed, you could deduce that that was wrong, just knowing that your pump rate is now giving you 15 MUs per minute if you're at 45. So you might have a math error or a med error on your hands. Not a huge difference, but if the nurse tells you that pit's at 11 and you walk in and the pit's at 15, something went wrong there, and you might have to talk to that nurse about it and say, I went in and I saw the pump rate set to this. Is that correct? Is that what I should be at? And of course, the first thing the nurse would do when you're looking at a pump rate that is either incorrect or the report was incorrect is look at your strip and make sure that your baby's tolerating this 15 MUs per minute. Because if the nurse thought it was 11 and someone else went in there and upped it, we used to have some docs who would do that. They got impatient waiting for a baby to deliver, and they would up our pit on us. We'd have to lock them out. You look at your strip first, and then you go talk to the nurse and clarify what's going on and find out what happened. So that might be something that you encounter. But really don't get too upset about Pitocin math in terms of a classroom exam. You should know how to work it out in dimensional analysis or ratio proportion, just so that if you're thrown a different concentration, you know how to deal with it. We're going to go on to our pit bolus for postpartum. All right, we're going to move on to some postpartum math. Okay, and this is a fairly common idea when we give pit in labor. We've already talked about it. Give tiny amounts. Pitocin, we want to flood that uterus with lots of oxytocin. It's going to contract and keep from bleeding. Okay, so we have whole units, not milli units anymore. So we want to know immediately after delivery, the provider orders the nurse to bolus a patient with 10 units of Pitocin over 30 minutes. You're giving a bolus over half an hour. The pre-mixed infusion bag, you're using the same bag that you used for induction, is 30 units of oxytocin and 500 mLs of 0.9% normal saline. The 0.9% is not in your problem. That's just the concentration of saline that it came in. What should the pump rate be? And then you need to know what the volume to be infused is. This is not the same because we're giving it over 30 minutes. So let's start with the first part of the problem, which is the pump rate. We have to set the pump rate. let's start with dimensional analysis. We start where we hope to finish. We have mLs per hour, right? So we want all of our mLs on the top and all of our hours on the bottom. So let's start with our mLs. We have this bag, 30 units and 500 mLs. Sorry for my sloppy writing. Let's put our 500 on the top and our 30 units, don't have to convert anymore because we're dealing in units, on the bottom. All right. Now, we have hours, but in the problem we're giving it over 30 minutes. Let's just make our conversion. We want our hours on the bottom, right? We know that 1 hour is 60 minutes, so we'll put that on the top. And now we have our 10 units. We don't want units and we don't want minutes, so let's do our 10 units and 30 minutes. Now we can start canceling out the measurement units that we don't need. Units, don't need units, don't need minutes. We just want mLs per hour. And so we have mLs, hour, mLs, hour, okay? So we have kind of what we need. Now, this is where the people who don't want to reduce fractions get annoyed. I don't like seeing so many zeros, but I'm going to work it out your way just so that you're not too upset. Those of you who understand the concept of canceling out your fractions and simplifying your math, feel free to do so, and I'm sure you've already kind of done that. Okay, but if you multiply straight across, you're going to end up, I know we sound so ridiculous, 300,000 mLs over 900 hours. Now get out your calculator, and you'll see that when you do 300,000 divided by 900, you end up with 333, and then it's a repeating decimal, 0.333, but we have to round it to the nearest whole number, mLs per hour, and that is your pump rate, okay? So that's the answer, 333 mLs per hour. All right, let's get rid of that now, because now we need the next part of our problem. Okay, so now that we know our pump rate, we want to find out how many mLs total we're infusing. So we need to start where we want to finish, which is mLs, not mLs per hour, just mLs. Okay, that's our volume. Okay, so we have, on this side of the equation, we have 333 mLs per hour. Okay, we know that 1 hour equals 60 minutes, and we know that this infusion is going to last 30 minutes. So now that we have it set up, you can cancel, okay, minutes and minutes, hours and hours. Now you only have your mLs left, which is what you wanted to end up with. At this point, you can either reduce your fraction, that 30 goes into 60 twice. You could make that a 1 and a 2. People who know how to reduce fractions, go ahead and do that. You'll get your answer faster. But if you don't like to do that, we'll just multiply straight across, because that's what people seem to want. So you end up with 9,990 over 60 mLs. When you get your calculator out and you divide that, you are going to end up with 166.5, which will then be rounded up to the nearest whole number, which is 167. Okay? That is your volume to be infused, to give you 10 units. All right? So that is how you would work out that problem. Okay, so now we have another medication. This is much simpler than the PIT math and the MAG math even. We have somebody who's getting Terbutaline. The patient is experiencing uterine hyperstimulation secondary to misoprostol induction. That hyperstimulation could look like tachycystole, which could look like more than 5 contractions in a 10-minute period. The nurse receives an order for Terbutaline, which is a tocolytic, 0.25 milligrams subcutaneously. Terbutaline comes supplied in the following vial. Looks like that. 1 milligram per ml. Okay. How many milliliters will you administer in this subcutaneous injection? Okay, so let's kind of work this out. We want mLs. We're starting where we hope to finish. Okay, you want mLs. What we have is 1 milligram per ml. We want mLs on the top, so let's put 1 ml over 1 milligram. And our dose is 0.25 milligrams. Okay, over nothing. So, using this, we cross out anything we don't want, which would be, we don't want milligrams, we just want mLs. We have to give 0.25 mLs. Now, here's the tricky part of this. That was not hard math, was it? No, not at all. Dimensional analysis worked really well for that. The tricky part is the answer will be wrong if you do not have a leading zero. A leading zero is a safety feature because if that little dot isn't very obvious, you could give 25 milligrams, which would be a tragedy. You would be giving 100 mLs of terbutaline in these little tiny vials. Who wants to pull 100 of those out, and what would that do to somebody? It's not a very smart thing to do. So a leading zero is necessary in any problem where you have a decimal dose that is not led by a whole number. If you have a 0.5, a 0.25, a 0.8, a 0.7, it doesn't matter. Anything that is less than 1 that is expressed as a decimal needs a leading zero, or it is wrong on a test. It is wrong in real life. All right? So that is that question. Okay, so labetalol is one of those things we could give in a hypertensive crisis in pregnancy. It is also a medication you will see on med-surg floors. So it's not strictly speaking OB math to do this problem, but the nurse is ordered to give labetalol, 20 milligrams IV push over 2 minutes. The dose is supplied as follows. It comes in this vial, which I'm going to now make giant. And I am going to call your attention to the dose, the strength that it's supplied in. Right here, 100 milligrams over 20 ml. Okay? It's also 5 milligrams over 1 ml. So see, they reduce their fraction. 100 over 20 is the same thing as 5 over 1. But you have a 20 ml vial. And I have seen it given in a vial that large. So, okay. Now, since we don't like to reduce fractions, let's go with that 5 milligrams to an ml. We need to give 20 milligrams IV push. Okay? So we need to know how many mLs, that was our question, will the nurse give. So we'll set it up. How many mLs? Well, we want the mLs on top. We have 5 milligrams to 1 ml. So 1 ml is the same as 5 milligrams. We'll put that there. We need to give 20 milligrams. All right. That's our dimensional analysis. Milligrams cancel. We don't need milligrams. We need mLs. So if we multiply across, we end up with 20 over 5. I hope you don't need a calculator to do that division, but that's exactly how you reduce a fraction, is you divide the bottom number by the top number, and you end up with 4 mLs. That is what you are giving IV push. Okay? Does that make sense? I'll just assume that it does, unless you text me or ask me in class. That's how you solve that problem. Now, some of you have probably been saying, Mrs. Mulcahy, I thought we were doing ratio proportion. I'll work this one out in ratio proportion so that you can see that either method gets you to the same answer. It's like if I gave you a map to the mall, but you followed your GPS. Whatever it takes to get you to the right answer, getting the right answer is the important piece. Okay, so I'll work this one out in ratio proportion just for giggles. Okay, so 20 milligrams over X is the same as 5 milligrams to 1 ml. It's also the same as 100 milligrams to 20 ml, but let's not get too fancy. Okay, so if we have 20 equals 5x, because we cross-multiplied, right? And now we can solve for x. Put everything, excuse me, hold on. Get that, whoops, sorry. All sort of attached to each other. Put everything over 5. You end up with that 20 over 5. That's a division problem. 20 divided by 5 equals 4. So we solved for x. That's the same thing as if you reduced a fraction. That's the exact same thing. That's what reducing a fraction is. But if it's, really your preference to multiply all the big numbers, do it. Just watch your zeros and don't screw it up, or you're going to hurt somebody. So here's another hypertension medication you might have to give as an IV push. In a hypertensive crisis, a nurse is ordered to give Hydralazine or Apresoline in 5 milligrams over 2 minutes IV push stat. The doses for pregnant women or postpartum women can be smaller than they are in the adult med-surg population, so sometimes the vial that's supplied in gives us something different and we have to calculate. So it comes supplied in this vial.
Purple thing in the jar.
What purple thing in the jar, babe? Oh, that's just laundry soap, honey. Okay. All right, so we have this dose. This is what we have. 20 milligrams per ml. Okay, so let's set up our problem. In dimensional analysis, we want mLs. We start where we hope to finish, right? So we know we need our mLs on top. If we have 20 milligrams per ml, our ml goes here, and since one thing equals another, our 20 milligrams goes here. It doesn't matter where we put the 20 milligrams. It can be on top or bottom, but because we want mLs at the end, we want our mLs on top for this problem. Okay, our dose is 5 milligrams. We want to know how many mil to give. Okay, so your milligrams cancel, they're unimportant. The 2 minutes, by the way, not important for the purposes of dosage calc. It will be important in a minute after you draw it up and you're standing at the bedside. But for right now, we just want to know how much did we drop in this syringe. So you end up with 5 ml over 20. When you do that, the rest of that problem, when you want to simplify that, you end up with 0.25 ml, okay? Because we're going to divide 5 by 20. 5 divided by 20 equals 0.25. Okay, and the important part again, remember that it will be marked wrong if you do not have a leading zero, because look at how little that decimal point is. Without a leading zero, somebody could assume, well, that's not enough. We don't give 0.25 on med-surg. It must be 2.5. I'll make a big old decimal point there, and then you give maybe 2.5 vials of this stuff when you were only supposed to give 0.25. So the leading zero is important. Okay. And that is another problem. Okay, so here's another dosage calc problem. We have a patient with Group Beta Strep, GBS. She's GBS positive. She comes into labor. She has an order for Penicillin, 5 million units, to be infused over 90 minutes. The dose comes up in a 250 ml bag of normal sterile saline. At what rate does the nurse set the pump, and what is the volume to be infused? Okay, so we want to know mLs per hour, again in dimensional analysis. Start where you hope to finish. mLs per hour. Now we need our mLs on the top. We have 250 mLs. That's our 5 million units, and we're not going to worry too much. We have a 250 ml bag. That's what we're going to worry about. We want to give it over 90 minutes. We know that 1 hour, we want the hour on the bottom, equals 60 minutes, correct? So how many mLs per hour? Well, get rid of what you don't need. Minutes to minutes. Now we have mLs per hour left. That's what we want. Okay. So again, you know, if you wanted to, you could reduce the fraction, but we're not going to do that. So when you multiply straight across, you end up with 15,000 mLs over 90 hours. If you divide 15,000 by 90, you will end up with 166.67, which we will round to the nearest whole number and make it 167 mLs per hour. Let me just kind of put a little box around that so you can see. That is our rate, 167 mLs per hour. The volume to be infused is right in the problem. It is 250 mLs. You're going to infuse the whole bag. The 5 million units is in 250 mLs. You infuse the whole bag to give the whole dose. So that is the volume to be infused. All right? Does everyone understand that? Good. So we can move on to another antibiotic problem. Okay, so 4 hours after you hang that 5 million unit bag, and every 4 hours after that, you're going to give 2.5 million units over 30 minutes. It comes up in a 100 ml bag. And you're going to have to set your pump rate, and you're going to have to set the volume to be infused. All right, so let's go back to dimensional analysis. Let's set it up the way we want to. We want to start where we hope to finish. So mLs per hour is what we want because that's our pump rate. Okay? What do we have? Well, we know that 1 hour is 60 minutes, and we want our infusion to run, our 100 mLs to run over 30 minutes. Okay? So we're kind of all set here. Cancel out the things you don't want. You don't want minutes. You just want mLs per hour. Okay? So you're going to end up with 6,000 over 30. Okay? Which at the end of the day is going to give you 200 mLs per hour. That's the rate. That is the pump rate. 200 mLs per hour. Now for the volume to be infused, you just look at the bag. You're going to give the whole bag. You want a whole dose. A 100 milliliter bag. Okay? It's hung as a piggyback. You have a mainline infusion. So that's what you need to know about OB math. I think you're in pretty good shape. I mean, we could do maybe one more. We'll do a site attack. So let's move on. Okay, so here's our next problem. You are ordered to give misoprostol 25 micrograms for cervical ripening. The dosage strength in the tablet is 100 micrograms. And now if you watched my lecture, you know what I'm saying about tablets are scored in half. This tablet is not scored for quarters, but this is what you're ordered to give. So calculate the correct dosage for this med. All right, so what we want is how many tablets? Okay, so you have 100 micrograms per tablet. Okay. And we want to give 25 micrograms. Micrograms cancel micrograms, so we have only tablets left. And going across, we have 25 over 100 tabs. Do that division, just make sure you're doing it right. To me, I look at it, I see 1/4. You are going to give 0.25 tabs. Now, it would not be wrong to say you're giving 1/4 of a tab. But if you do it as a decimal point, if you're expressing it as a decimal point, I know I'm getting a little repetitive, you do not want to forget this leading 0 because it will be marked incorrect. And that is all the OB math that I think I can give you. It really isn't specific to OB. It's just the same math that you've been doing applied to problems that are maybe a little wonky in terms of the number of conversions. But if you have any questions, see me in class, and we'll work out a few more. Thanks.